This is an epic question where we're trying to work out the fraction of this octagon that's shaded, a ceramic design by Antoni Gaudi. So 8 lines drawn, and then we divide the outer octagon into 3 equal parts using these lines. So there's two approaches to this method, using lengths and somewhat thinking about the angles, which is actually how I did it. And then instead trying to construct a shape inside the octagon that is like repeated throughout and from which we can read off. That can often be the best way to do this sort of question. Um, and yeah, it's just the simplest way. So I personally struggle with this. I just get into calculation mode, but I am going to share how you can do it using this first method, and I'll talk about my other method. So, right, let's join basically split the octagon into two in lots of different ways. So here to here, here to here. Okay, so they will necessarily all go through the center. And what we've managed to do is create 8 large triangles. Okay, let's just focus on one of them, the one at the bottom. Now, if I draw a line coming across like this, then I start to see it. I seem to be making like a smaller triangle inside, a bit like how you can split an equilateral triangle into more equilateral triangles. That is a fact that is very useful in these sorts of challenges. Here, these are not equilateral because the angles in an octagon are 135, so the base angle here is 67.5, but that doesn't mean you can't split it up in the same sort of way, like this. And in fact, we're basically there because we have 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles. 2 of them are shaded, and this repeats throughout the other 7 triangles. So throughout 2/9 of the shape is shaded, and that's the answer. Well, that seems very quick and easy, but of course that is not obvious to take that step. Well, it wasn't at least for me. And second point is, how do we know that these triangles are necessarily all the same? So I'm going to talk a little bit about that before I talk about my second method of doing it, but it is actually that simple ultimately. Um, okay, I'm just going to label these angles green because they're the same. They're actually going to be 67.5 each. And because we're splitting it into 3 equal parts, let's say like each one of these is 1. So I can do that to start with. Now I'm going to have a purple angle up here, whatever I get. Actually, I think it's going to be 118 minus 130, so it's going to be 50. But then, if I start looking at the lines, I can see that there's lots of parallel lines. Like this blue line here, for example, is parallel to this one. Like it must be. And if I was to sort of carry it on here, then yeah, I could create more parallel lines. So I can use that to help me show congruency. For example, I've sort of, I'm just trying to make sure that I've got my argument really careful. So we've got green, green, purple, and length 1. And then we've got length 1 here. Um, Now, where do I have? I got some Zs in different places. So, for example, this is a Z. Okay, yeah, now we're off, which means that this angle up here is also going to be green. And I can make a similar argument over here. What else do I have? Ah, here's a Z, so this will necessarily be a purple angle. And then that one will also be green. And then because, oh, sorry, let me carry on with the angles. I can follow a similar sort of line of argument and get all of these angles as purple. They're all the same, and these ones as green, using the idea of parallel lines. Now, because we're sharing like multiple sides and we have angles the same, then actually this bottom row must necessarily all be congruent triangles. Then we can carry it on in the same sort of way. This one, like we know that 2 greens plus a purple gives 180, so this must also be green. Um, and this one's purple, and then this must be green, and so on. And basically, we can work our way up and show necessarily. I mean, this is something you should do if you're being extra careful, and if you're in like an Olympiad competition, you need to justify. You can't just say, "Hey, these are congruent." But using this line of reasoning, we can show that all 9 triangles are congruent, 2 are shaded, and therefore it's 2 over 9. Now here's a second way of doing it. I was actually quite proud of this method until I saw how simple that other method was. Okay, so what I did is I took the octagon and I decided to find the total area. I said that, as I did a minute ago, I said that each of these lengths is going to be 1, which means the sides of the octagon are going to be 3. So for example, this is 3. And then I can spot, I've got a right angled triangle here, and let me label this length x and this one x. Then I can use Pythagoras to say that x squared plus x squared, or 2x squared, is equal to 3 squared, or 9. And therefore x squared is 9 over 2, x is 3 over root 2. Because then the length of the square is going to be 3 for this part, plus 2x. Now 2x is going to be 2 times 3 over root 2, and you can either consider rationalizing the denominator. You times the top by root 2 and you times the bottom by root 2, and then the root 2 cancels with the 2. Sorry, the root 2 times root 2 becomes 2, cancels with the 2. Or you can understand that 2 divided by root 2 is just root 2. In either case, we get 3 root 2 now. So 3 plus 3 plus 3 root 2. So the area of the octagon is going to equal 3 plus 3 root 2 squared, for the whole area of the square. But don't forget, we then need to subtract these 4 triangles. So minus 4 times a half times, it's going to be half times x squared. So 3 over 2 all squared. Expand the bracket, you can see this is more complicated, it's got to be said, but it's still going to work out. 9 plus 3 times 3 root 2, 9 root 2 plus another one is 18 root 2. 3 root 2 times 3 root 2 is 3 times 3 root 2 times root 2, so 9 times 2, so 18. Then, sorry, I'm going to minus along the way, so 4 times a half is 2, so 2 times 9 over 2. This is just going to give 9, so these two are going to cancel, and we're left with 18 plus 18 root 2. I found the area of an octagon. Right, now we just have to work out the area of the shaded region. Okay, that does feel a little bit daunting. And here's how we can do it. There's a slight flaw in this method, which I'll talk about, and it is again to do with proving congruency. So what I noticed is if I drew this blue shape first of all, I thought, okay, maybe I can split it up into triangles that are the same. And then I can see that I've got 2 triangles here, and then there are 8 sides to this. I've basically got 16 triangles. What I did is I assumed that they were all the same and that they were the same as the blue one up here. Now, it's since been I've since shown that they are all congruent, but to show they were congruent, we had to draw it as this. And once you get to this point, you can see straight away that it is 2 over 9. So when I did it, I didn't actually prove. I mean, remember, you're under time conditions sometimes. So in terms of like the IMC, this is okay, making a good attempt at the last question, even if we're kind of saying, oh, I just hope that the triangles are all congruent. So let's take one particular triangle and draw it out. So we know the base is 1, but what about the height? Now remember, from before, we showed that the height of the whole octagon was 3 plus 3 root 2. And now you see we've got 1, 2, 3, 4, 5, 6 triangles. So if I'm saying they're all the same, I can take my 3 plus 3 root 2 and I can just divide that by 6. So the height of each triangle is going to be a half plus a half root 2. That's kind of the leap I made without proving congruency, because now we're basically there. It must be that the area of one triangle is a half times base times height. And then I've got 16 of them. So I can do 16 times a half to give 8. And then half times this is going to give me 4 plus 4 root 2. So overall, I've got 4 plus 4 root 2 for the area of the shaded region, divided by 18 plus 18 root 2 for the area of the octagon. I can factorize out a 1. Well, sorry, I'll factorize out 4, 1 plus root 2. I'll factorize out an 18, 1 plus root 2. These now cancel, 4 over 18 or 2 over 9. So hey, look, I think it's still a good method to discuss. Um, you know, it's a tough question, and I'd be interested to see other methods for solving it. Like, I momentarily thought, oh, could I work out the area of these things? That just didn't. Well, I've worked out that one, but like this sort of thing, that didn't seem the way to go. But anyway, yeah, well done on this challenge, and really good question.